This video is on energy and light equations. So light has a wave-like property as it travels through the air. A light wave has some different parts to it. We have the wave here going along an amount of time. The distance between the middle and the top of a wave is called the amplitude, which is the height of the wave, and that is labeled as an A, capital A. The distance from peak to peak, that's how we measure the wavelength, shown by the symbol lambda. Okay? This is measured in nanometers. Remember that 1 nanometer, or 1 meter, has 1 times 10 to the 9th nanometers inside of it. The number of waves that we have, going from here to back up, is considered to here as 1 wave. So the number of waves that we have per unit time is our frequency, shown here, a little curvy V. The frequency is in units of 1 over second, so the number per second, so inverse seconds, or hertz, which is Hz. We can have high frequency, where we have many waves per unit of time, or a low frequency, where we have a less number of waves per unit of time. We have a light spectrum that goes from low frequency to high frequency. Radio waves are going to be your longest wavelength. They're the waves that travel through the air to give you your radio station. Microwaves, these are the waves that you use in a microwave to cook your food or popcorn. IR stands for infrared. Then we have our visible region. This is in the times 10 to the 9th region. In our visible region, it goes from red with the lowest frequency to violet with the highest frequency. Then our UV region, followed by X-rays, and then gamma rays. Now gamma rays penetrate through your body, pass completely through your body. And we'll learn more about these in our nuclear chemistry unit. X-rays, these are the kind of rays, the light waves, that travel through your skin to look at your bone when you go to the doctor to get an X-ray. Okay, so these being our highest frequency to lowest frequency. Light has a unique property to it. The speed of light is always constant at 2.998 times 10 to the 8th meters per second. All light has the same speed. You notice that as the wavelength decreases, our frequency increases. So as our waves start to get closer and closer and closer together, that means that I'm able to have more waves per unit of time. So wavelength and frequency have an inverse relationship. Our wavelength multiplied times our frequency is equal to our speed of light. We abbreviate the speed of light as the lowercase letter c, again 2.998 times 10 to the 8th meters per second. We can now write an equation for the speed of light. Speed of light is equal to wavelength times frequency, or lambda times nu. Okay? So to do light equations, we just use our equation here for light. An example problem is, what is the frequency of light if light has a wavelength equal to 450 nanometers? Knowing that our speed of light is 2.998 times 10 to the 8th meters per second. Notice that our light is in meters per second, but our wavelength is in nanometers. Now we cannot compare meters to nanometers. We need to convert. It's easiest to convert our 450 nanometers to meters as opposed to converting this number to nanometers. So we start by doing that, converting our 450 nanometers, using our unit cancellation, 1 times 10 to the 9th nanometer per meter, which gives me 450 times 10 to the negative 9th meters. Then I arrange my equation to solve for frequency, dividing both sides by lambda. So I get frequency is equal to speed of light over lambda, which is my wavelength. I plug in my variables that I know. My speed of light is 2.998 times 10 to the 8th meters per second. My wavelength is 450 times 10 to the negative 9 meters. When I plug this into my calculator, I get a frequency of 6.66 times 10 to the 14th inverse seconds, or hertz. Example number 2. What is the frequency of light emitted from an electron relaxing from n equals 6 to n equals 3. This is where we go back to our Bohr model of the hydrogen atom and locate an electron relaxing from the outer energy level of n equals 6 down to n equals 3. From here, we can then find what wavelength of light is emitted from this relaxation. So, from my hydrogen atom Bohr model, we see that from n equals 6 to n equals 3, our electron emits a wavelength of light equal to 1,094 nanometers. We know that the speed of light is equal to 2.998 times 10 to the 8th meters per second, and I can use my speed of light equation where c is equal to lambda times frequency, solving for lambda to get speed of light over frequency, plugging in my variables 2.998 times 10 to the 8th meters per second divided by my wavelength of light, which is now converted into meters, of 1094 times 10 to the negative 9th meters. When I do that, I get a frequency of light to be 2.74 times 10 to the 14th inverse seconds. And this is how I solved for turning nanometers to meters. Go ahead now and you try to find the wavelength of light that has a frequency of 4.75 times 10 to the 12th inverse seconds. Remember to use our speed of light equation of c equals lambda times nu, which is my wavelength times the frequency, to rearrange my equation for what I'm looking for. That's my my wavelength of light, lambda. Then to plug in my variables, solving for my wavelength, which will be in meters, and then converting from meters to nanometers.